All right, I think we're rolling. Yes, indeed we are. So today we learned about the quotient rule. Can you name all the seven dwarfs? Which one doesn't end with a Y? That's the other question. Always asked about the seven dwarfs. What's that got to do with anything? Everything. Here we go. So the quotient rule is used when you want to take the derivative, that's what this part says, of something that is one thing divided by another, two functions. And the way we do it is we take the g of x and we multiply it by the derivative of the f of x. And then from that we subtract the f of x multiplied by the derivative of the g of x, and we put that whole thing over the g of x squared, or if you like, denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. If you like that, great. If you're not sure about that, you might like this. Okay? So instead of saying f of x over g of x, we'll use a little Snow White thing, hi ho, hi ho. So hi is the top one, ho is the bottom one, and it's just, or some people say high over low, but I like high over low because. All right, so here's how it works. Ho, d high, minus high, d ho, all over ho ho. Okay, so ho is the bottom part, g of x, times the derivative of high, which is the f of x, minus high, which is the f of x, minus d ho, or times d ho, which is the derivative of the denominator, all over ho ho. So ho d high minus I d ho over ho ho. That's much easier to remember. It's kind of catchy. Okay, ho d high minus I d ho over ho ho. That's the quotient rule in sort of a way that's easy to remember. If you like, g of x times f prime of x minus f of x times g prime of x all over g of x squared, that's great. But ho d high minus I d ho over ho ho sort of works. You know, think hi ho, hi ho. All right, anyway, off we go. So I think, if I'm not mistaken, this probably says that, right? There it is. So there it is, the quotient rule right there. Ho, d high minus I, d ho over ho ho. Okay, love it, live with it, learn it, go. All right, so here's what we do. We go ho, we're going to find the derivative of this thing here. Ho, which is the bottom part, 2x plus 5, t high, which is the derivative of the top part. The derivative of 3x squared plus 7x is 6x plus 7, minus high, which is the 3x squared plus 7x, d ho, which is the derivative of the bottom, is just 2, so that's nice, all over the bottom squared. And instead of writing ho ho, I would just write ho squared. Okay, 2x plus 5 squared, that's what ho ho is, so times so. So we've got a nice little expression there. We've got to get ourselves working our way a little bit further along. So we'll simplify this and use our distribution 12x squared plus 30x plus 14x plus 35 minus 6x squared minus 14x all over 2x plus 5 quantity squared. Simplify the top. I'm going to leave this bottom because leaving the bottom in that form is going to be more helpful to us as we move along. If we want to find out when the denominator of my derivative is equal to 0, which should give us some indication when things aren't differentiable, it's easier to tell in this form. So we leave the denominator as it is. Let's gather up what we have here. 12x squared minus 6x squared. Let's see, so that turns out to be 6x squared. 30x plus 14x is 44x. Oops, wait, hold on. Let's undo that. Let's undo this. Oh, crap. So 6x squared. I got 30 plus 14 is 44, minus 14 more. So that probably leaves me at just 30x. And then I've got plus 35. So all over 2x plus 5 quantity squared. And that is a perfectly delightful way to write the derivative y primed or dy dx or something like that, dy dx. Okay? Derivative, product rule. We'll get a bunch of practice with it. And it never goes away. So we can take more than one derivative. We call them higher order derivatives. If I start with something called like y equals x to the fifth, blah, 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 blah. The first derivative, 5x to the fourth, plus 24x cubed, minus 24x squared, plus 24x, there's a lot of 24s, minus 15. Great. Now, second derivative. Just take the derivative of the first derivative. 5x to the fourth becomes 20x to the third. 72x squared. 48x. 24. Now, so we get less and less terms as we take the derivative because our constant goes away. Third derivative, which we, the second derivative is the rate of change of the rate of change, which is sort of important to us, tells us how we're changing. The third derivative is just pure fun. 60x squared plus 144x minus 48. If we wanted to, we could go to a fourth derivative. We could go to a fifth derivative, but we never do. Third derivative is probably the furthest we ever go, and really we spend a lot of time with first and second derivatives as we go through this higher order derivatives. So in terms of like physics-y stuff, position, okay, h, velocity is the derivative of that. So velocity is the derivative of my height or my position with time is equal to velocity. My acceleration is the derivative of my velocity with time, which is the second derivative of my position with respect to time. So these all are sort of related to each other through the derivative. So the rate of change of position is the velocity. The rate of change of velocity is the acceleration. So the rate of change of the rate of change of position is the acceleration. So there you have it. All right, oops, there's that. You can go back and see that. That's just really cool, but I don't know if that's really the problems that we're doing. All right, so let's review. All right, we see that. The big thing, quotient rule. Hody high minus hidey ho over ho ho. Hody high minus hidey ho over ho ho. Say it. Say it with me one time. Oh, I didn't say it, did I? That's about all. Oh yeah. Okay. Haiku. And you? Done. Thanks for watching. Hope you learned something. Practice, practice, practice.